Hello, this is a lesson in physics. Today we are talking about the force between a point charge and a uniformly charged rod. This rod has finite length of capital L. So this is the diagram. This is the rod. The length is capital L. The charge on the rod is Q2, uniformly distributed over this entire rod. There is a point charge Q1. Q1 is located on the perpendicular bisector of the rod. Therefore, this part is 1/2 of L. This part is also 1/2 of L. What is the force on Q1 due to the charge Q2 over the rod? We start with Coulomb's law. But Coulomb's law is a formula for the force between two point charges. I now have one point charge, but the other one is a rod. So I cannot use Coulomb's law for a rod. So I need to divide the rod into many small parts. This black part is a small section on the rod. This small section, of course, carries a charge. And certainly this charge is not the total charge. The charge on this part is not Q2, right? It's a fraction of Q2. Let's write down the Coulomb's law first. The force between two charges is equal to constant K. K is 9 times 10 to the exponent 9. It's a constant. K times the product of the two charges. One charge is Q1. Another charge is the charge on the small section. We call it delta Q. So, Coulomb's law. K times the product of the two charges, Q1, delta Q, divided by the distance between them squared. The distance between these two charges, let's call it R. So divide by R squared. Next, we need to find what delta Q is. We use proportion. For a length capital L, the charge is Q2. But now the length is not capital L. The length is delta X. Delta X is the length of the small section on the rod. So it's a proportion. For length capital L, the charge is Q2. For length delta X, what is the charge? If you know how to do the proportion, then delta Q should be should be this. There is a meaning of this expression. Q2 divided by L is the charge per unit length of the rod. But the small section, the length of the small section is delta x. Therefore, the charge of the small section is Q2 divided by L times delta x. It's just a proportion, it's a ratio problem. So rewrite this. R squared is equal to y squared plus x squared. It is nothing but Pythagoras theorem. R squared is y squared. I call this distance x. It's Pythagoras theorem. I write the left-hand side delta F. Delta means a small quantity. Why this force is a small force, small quantity? Because this force is not due to the entire rod. This force is due to only a small section. So it's a small force due to a small section. So this small force is this now. But I don't want a small force, I want a total force. Due to the entire rod, what is the force? So can I add delta F? The answer is yes or no. If you can add the vector, because this is a vector. If you know how to add vectors, of course it's okay, you can add vectors. But to add many quantities together, we use integration. Remember, integration is the sum of magnitudes, not vectors. So we cannot use integration to add vectors. Then what do? We have to decompose the vector delta F into its y component. I call this vertical direction y. You need y component and x component. You decompose it. Then once you have components, each component represents a number, a magnitude. Then you can do integration on the y component, and you can also do the integration on the x component. Now here, this problem is symmetrical with left and right. The right-hand half and the left-hand half are symmetrical. The right-hand half will push the point charge Q1 to that direction, right? Correct? And the left-hand side of the rod tends to push the point charge Q1 to this side. Do you catch the idea? This part of the charge will push the Q1 that way. This part of the rod will push the Q1 that way. Therefore, the charge Q1 cannot go both this way and that way. It's not possible. So the result is going that way. In other words, from this conceptual argument, the x component, if you add them together, the x component due to this, due to another section, due to this section, due to this section, you add all the x component due to various sections, the x components cancel each other. Because our argument tells us it cannot go sidewise. It has to go up. Therefore, only the y component is important. So we do the y component. Y component is this magnitude times the cosine theta. Then you have delta Fy. So write down the cosine theta here. Then what is cosine theta? Look at this right triangle. Cosine theta is adjacent divided by hypotenuse is y divided by r. R is y squared plus x squared take square root. Therefore, this is my cosine theta. Combine this part and this part, I have the bracket goes to the exponent 3/2. Now, because this is already the y component, you need to add all the y components due to the small sections. So you add. I can use a label, summation sign, to represent addition. Summation sign. And why do I use I, subscript I? Because this delta xi can represent various small sections. So I can call this, if I start from this end to this end, I can call this delta x1, and the next delta x2, and the next delta x3. So usually we do this. We divide this into n small sections, n. Therefore, the subscript I goes from delta x1, delta x2, delta x3, up to delta xn. So the summation sign is the subscript I changes from 1 to n. So that's the summation notation. And you need I here, and I here. So I explained delta x1, delta x2. What is x1, x2, x3? So x1, suppose you call this section the number 1 section, then x1 is the distance from the center to this. This is x1. Then the next section, x2 here, x3 here, x4 here, and so on until from here to here is xn. So this is the summation. But if you add all the small section contribution, the result is still not yet exactly the force. It's still not, because you are having small sections. Only when you divide the rod into infinite number of sections, that means each section, the length delta x will approach 0. Only under that case, then the summation is exactly the y component force you want. So we need to take the limit. The limit means the number of sections becomes infinity. So take the limit, n goes to infinity. Once you sum and take the limit, this is the fundamental theorem of definite integral. Now, the writing here is from calculus textbook. Okay, we are applying calculus, the fundamental definition of fundamental theorem of definite integral to our physics problem. So now with limit and summation, we have integration. So I write integration now. This is, remember, definite integral. For a definite integral, you have the lower limit, the upper limit. What is the lower limit? What is the upper limit? The lower limit is where you start, and the upper limit is where you end. So where do I start? I start this small section here. This is where I start. And I sum, and this is my end. So at the beginning, what is the x value? X value is this. Because this is 0, I take this as 0. You see this x? X is measured from center, 0. So what is the x value here? It is half of this, but it's negative, right? Because it's on the left side of my 0. So the lower limit is negative L over 2. The upper limit is positive L over 2. So that's the result. Then look at the inside, look at the function after the integral sign. What is the function we want to integrate? This is the function. The function is this, 1 over this. Huh? This is a function. Look at x. X is squared, which means if x is negative 3, you have a value, and when x is positive 3, you have the same value. So negative x and positive x doesn't make any difference. This is an even function. You see? X squared is an even function. X squared is an even function. So this part is an even function. This part has a name, which is called integrand. If you learned integration, you know this name. This is called integrand. So our integrand is even. So if you integrate an even function from negative a to positive a, then you don't need to do that. You can integrate from 0 to a and multiply by 2 because it is an even function. Okay. Therefore, I rewrite the two limits, upper limit and the lower limit, change the lower limit to 0 and multiply the entire expression by 2. This is what I want to achieve. I want to integrate this. And you see, probably you think, oh, I don't know how to integrate this. It has 3 over 2 power and looks quite complicated. I don't know how to do it. All right. You can do 2 ways. One way is to go to your textbook, calculus. Go to near the end of the textbook. Usually in calculus textbook, at the end, there is a table. It's called the table of integrals. And you have many different integration, and the answer is given there. You just go to the table and find the answer for this kind of integration. So you use the table of integration. That is easy. But suppose you don't have the table, then what do? Then we need to do something which is called change of variables. Yeah, you can still do this. Okay, the next step, I will show you how to use table integrals and as well as how to do mathematically without using the table. So I need to erase something now. Okay. Let me see what can be erased. So I must leave this because this is what I want to do. Okay. So first, let us do this by using table of integrals. There is a formula. The formula is this. From the table, there is a formula. U squared by A squared. So from the table of integrals, this is the formula I found. This integration, the result is this. Of course, you have integration constants, constant of integration, because this formula is indefinite integral, so you need a constant of integration. Now, this expression is exactly this. So I can use this formula for my problem. So what is the result if I use this? Then, okay. Okay, so I have I apply the formula and I get this result. This is just the result of the formula. So this. Remember, this is not an indefinite integral. We have definite integral, we have lower limit and upper limit. So after you use the formula, you write down the lower limit and the upper limit. When you substitute the lower limit in, this entire expression is 0 because x is 0. When you substitute L over 2 into x, then we have the next. I don't need to erase that. you substitute the upper limit into the expression, and this is what you get. Two, this two and this two cancels. The L cancels. So y cancel one of the y at the denominator. So what do we get? So this is what you get, finally. And this is our result. Although this is a result of the y component, since we discussed from the conceptual argument, the x component cancels out. So the y component result is our final result. So this is our final result. Let us discuss this final result. Suppose the Q1 is very, very far away from this rod. Very far away. What does that mean? That means y is very large. Very large compared with the length of the rod. The length of the rod becomes so small if you are if you draw the sketch with very large y. So when y is much, much larger than L, that means Q1 is very, very far away from the rod. If this is the case, y is much, much larger than L, and then of course y is much larger than half of L. Huh? Now you look at this. If y is much larger than half of L, then half of L compared with y can be neglected because it's so small. So you neglect this, and the inside of the square root is y squared. You take the square root, you get y out, and you already have a y at the outside, so y times y is y squared. So under this condition, you have under this condition, you have this result, right? I need to separate this, okay. Under this condition, the force in the y direction. Force is in the y direction, and the force is given by this. Look at this. What is this? Newton's law, the Coulomb's law between two point charges. You see? Q1, Q2 are point charges. The separation between them is y. So when they are so far apart, the long rod appears very small, just like a point charge. Therefore, the formula becomes Coulomb's law for 2-point charges. Okay, this is when you use the table of integrals. Next, you do not use the table of integrals. Let's see how much time we already spent. I don't want to spend each lesson too long. I'd rather continue with the next lesson. But we can still discuss something. We use physical argument. We use conceptual argument to say that the x component will cancel each other. So the resultant force is only in the y direction. But can we do mathematically? Of course we can do mathematically, okay? So let's see now this. Here, y component is cosine theta. What is x component? X component, this side is sine theta, right? Sine theta. So the x component is sine theta. So let me change this. X component is not cosine theta, it's sine theta. And I need to change the subscript. It's not y, it's x. Okay. Let me erase the formula from table of integrals. Okay. Now let's not do the full writing. Let's skip the summation writing with summation, and we skip the limit. So we go directly into integration, with the understanding that you need to add many x components, and it takes a limit. Delta x becomes infinitely small, or you say infinitesimally small. So fx write the constant part. Now we integrate delta x becomes dx. Okay, sine theta, and you have dx. This. All right. We can use this diagram to change the variable x into theta, because you cannot integrate if you have variable x and also variable theta. You cannot integrate with two variables. So you need to change theta to x or change x to theta. Oh, okay. So let's see this now. Let's erase this. Okay. Go to this triangle. It's a right triangle, right? So you have a Pythagoras theorem. But Pythagoras theorem doesn't involve theta. So I want to involve theta. What is x? X is x over y is tangent theta. So x is y tangent theta. This is r. Let's see now. This is r. Okay. So I can replace this by r squared. Right? Yeah. Because y squared plus x squared is just r squared. R squared is here. How is r related to theta? So y over r is cosine theta. Therefore, r is y secant theta, right? So suppose we put these into that. See what happens. Okay. Let's see. X over r sine theta. Yeah. Yeah, okay. So I don't need that. Yeah. Sine theta is this over that is x over r. So put that in. Sine theta is x over r. So I have x over r. But I have r squared there, so it's r cubed dx. Okay. So I need to integrate this. Because this integration is dx, so the limits should be x. So what is the lower limit for x? Is negative L over 2, and what is the upper limit for for x is L over 2. Look at the integrand x over r cubed. From here to here, x will be negative here, x is positive here, so x itself is an odd function. What about r? R is hypotenuse. Hypotenuse has no negative, no positive, right? You don't say this side r is negative, right? Only the x value is negative, not r. R is always positive. So x will change from negative to positive, so it is odd. This integrand is an odd function. Now you integrate the odd function from negative, say negative 10 to positive 10. What do you get? You get 0. You don't need to do it. It's 0. If your integrand is odd function, and your upper limit and lower limit is from minus, say, minus a to positive a, then it's 0. We already mentioned if the integrand is even, and you integrate from negative a to positive a, then you get the double of from 0 to a. You understand? These are the results of calculus. So you can use this way to show that the x component adds up to 0. So the y component result is our final result. So I think this is a long enough lesson. So I will give you the same question, but do not use the table of integrals. Of course, we get the same result. If we do not use the table of integrals, how do we do that? It's very, very similar to that. Very similar, except slightly different point of view. That's it. The writing is almost the same. So I leave this to you next lesson. Thank you for watching. Goodbye.